Today we are going to design a concrete beam. For that you can adopt three methods: working stress method, ultimate load method and limit state method. Okay, and limit state method is the most currently used and considered as the most accurate one compared to other two methods. So we are now concentrating on limit state method. What is limit state method? Before that, what is limit state? Limit state is just the acceptable limit of collapse and serviceability requirements before failure. Okay, if you take a beam or any concrete structure, for just before breaking or just before failing, there will be a limit state. Okay, at the verge of, at the fringe of breaking, and we are considering that limit state for designing this beam. Okay, so we will gather all the informations and knowledge that we can get about the loads and the strength of this beam, and we will assume a limit state, and using that limit state we will design a concrete structure. Okay, there are mainly two types of limit states. Limit state of collapse. Limit state of collapse means its stability and safety primarily. That is the primary important. That is of primary importance. It shouldn't break at any case. The people under this beam or roof slab should be safe. That safety is the main priority, obviously. So limit state of collapse will be concerned about safety and stability. Okay, and the second one, limit state of serviceability. Okay, even if it attains a limit state, there will be a deflection, right? Deflection means if this was a beam, there can be a bending like this, and this is deflection. If it bends like this, a deflection happens. Okay, even if a case of deflection occurs, it shouldn't be over limit. It should be repairable, or maintenance should be possible. Okay, so limit state of serviceability, we are concerned about deflection and cracking. Cracks can develop, but it shouldn't be excessive. Okay, so this is the most important 2 points about limit state method of concrete structures. Okay, so we'll keep it at here, and we'll come to the real issue of designing. Okay, so leave all the theory we have just told you. Consider this as a beam, and this dimensions we want to design. So right now it is an imaginary beam, and there are two factors, right? There will be loads. Suppose this is a beam, I know how much load there will be coming. Okay, so load is of primary important. Okay, maybe if it is a residential building, there will be people standing in this beam, there will be a cupboard, a kitchen cupboard or anything. There will be many furnitures or load will be here. Okay, so there are many chances of having an enormous amount of load. Okay, so this is the point. When we want to design a beam, okay, when we want to design a beam and we know there will be load X. Okay, we know if this is the beam and we know the load value X. Okay, how will you design it? Will you just design it for x, or will you design for a value greater than x? Obviously, we will be designing a value greater than x. We will consider if, for example, the load is 30 kilonewton per meter. That is the maximum load that could attain. Okay, at our probability study. Okay, and our best possibility will be, we'll multiply it with some factor, and we'll suppose we'll design the beam for 45 kilonewton per meter, right? Okay, so we know there won't be any load above 30 kilonewton per meter, but even though, for the sake of safety of this beam, we will design it for a much higher value. It's just an approximated value, 45. It can, if we are designing it for 60 kilonewton per meter, it will be more safer, right? So you need to amplify this load factor. Okay, that is the theory behind, that is the key point. Okay, and for that we have some terms. First one, characteristic load. Characteristic load means the probability of having the load not exceeding 95% of the time. If suppose 30 kilonewton per meter is the characteristic load considered for this beam, 95% of the time of this lifetime of this beam, it will not exceed 30 kilonewton per meter. Okay, that 95% value is important. Okay, I hope it's clear. If it is characteristic load, is the load, that load won't be exceeded 95% of time. Okay, 5% it's a chance, it's a probability. Okay, so that is characteristic load, and we want to get a load for design. Okay, so what we want to calculate is design load. Okay, so with the example I last told you, with 30 and 45, design load will be calculated by characteristic load multiplied with a factor, and that factor, that is the key point in limit state method, and that factor that we multiply with load to get our design load is partial safety factor. Partial safety factor. Okay, in this case we call it as gamma F. Okay, usually gamma F can be 1.5, and the accurate values can be traced from IS 456. There is a table for tracing this gamma F's for each and every type of loads. Okay, so if this is 30 kilonewton per meter, we will multiply it with 1.5 to get 45 kilonewton per meter as our design load. Okay, and we know it won't be exceeding 30 for the 95% of time. Even then we are designing for 45 kilonewton per meter, and so that it will be stronger for longer period, and it will be safe, and we will be assured that it is safe. Okay, I hope it's clear. That's the only thing you need to know about load. Okay, so this is the equation. And second one, the load is acting like this, and there will be a resisting forces which will be resisting this load, upcoming load. and this we call it as strength. Right, that strength we will be deciding. We will be deciding on the quantity of or quality of concrete. We will be deciding on the quality of steel. We will be deciding on the dimension. We want to know the dimension like this. We want to know how much of reinforcement is here. Okay, all those things we need to know, and our assumption is we need to have all these dimension and steel reinforcements so that you have the strength to resist this much design load. Okay, I hope it's clear. Okay, so next one is strength. So what composes of strengths? What are the things that you need to consider for strength of a RCCB? As you can see, yes, RCC is composed of two things, right? Which are they? Concrete and steel. Right. Concrete strength is said to be as FCK, and steel strength is said to be as Fy. Okay, if you don't remember, FCK value will be 20 Newton per mm square for M20 concrete. For M25 concrete, it will be 25 Newton per mm square. Okay, that will be tested by a universal testing machine, as we said earlier, for a 15 centimeter side cube, concrete cube. Okay, and steel will be, if it is Fe 415, Fy will be 415 Newton per mm square. Okay, so these are the two things. These are two examples. It can change. FCK can be 15, 20, 25, 30, 35, 40, etc. You can go like that. And Fy can be three values: 250, 415, and 500. Okay, this value can be either of these three. Okay, so that's that. And these are the two things you need to consider. Two materials that impart strength to RCCB. Okay, in that also, this FCK and Fy are known as characteristic, not load, strength, characteristic strength. And this characteristic strength is the strength of concrete in case of concrete and steel in case of steel, which will not go below 95% of time. Okay, if 20 Newton per mm square, if the characteristic strength of concrete, if we test 100 samples, more than 95 numbers will have 20 Newton per mm square. That's it. Okay, if you test the steel 100 samples, more than 95 samples should have the strength of 415 Newton per mm. Then only you can call characteristic strength as 450 for steel and 20 for concrete. Okay. So FCK and Fy you know right now. And then again that logic of here. Okay, if this is the beam and we know the strength, actual strength FCK and Fy, that is comprising of these materials in this RCC beam, and how will you consider it as design strength? design strength is equal to, how will you consider that? Will you multiply it with a value, or will you divide? Suppose M20 FCK is 20 Newton per mm square. Okay, so considering only concrete, it is 20 Newton per mm square. So with experimentally we know that it will endure 20 Newton per mm square compression. But will we design for that? No, we will design for a lesser value, maybe 10 or maybe 15, maybe 12 Newton per mm square. So that we want to have a confidence that if you design the beam for 12 Newton per mm square, we are very confident that it will retain as it is having 20 Newton per mm square. Okay, so in case of load, we will maximize by multiplying with the partial safety factor, but the same partial safety factor we will use in here, but we will divide it. Okay, we will divide FCK so that it gets reduced, and we will divide Fy so that it will get reduced. Okay, you get the point. Okay, so design strength will be characteristic strength divided by gamma m. In this case it is gamma m. Okay, this is the theory you should know. And in case of concrete, design strength is equal to FCK. FCK is the characteristic strength of concrete divided by, for concrete, partial safety factor is given as 1.5. Okay, and steel design strength is equal to Fy is the characteristic strength of steel divided by 1.15. 1.15 is the partial safety factor of steel. Okay, so FCK you will get 0.67 FCK. Okay, and you will get this as 0.87 Fy. I hope it's clear. We have only two materials, steel and concrete, in RCC beam, and you will divide it with partial safety factor. 1.5 is the partial safety factor for concrete and 1.15 for steel. Okay, and one more minute point, as it is a rectangular beam, always it will be different shapes. Okay, the different should be noted that whenever we check this characteristic strength, it is a cubical shape of 15 centimeter, as you remember. Okay, so the strength that you get from this cubical shape is given as FCK 20, in case if that is M20 mix, but it may not be the same in case of a rectangular shape. So to consider for that shape factor, we will again divide it with the partial safety factor 1.5. Okay, so actually the design strength of concrete is 0.466 FCK. Okay, so as our general rule, we will divide FCK by 1.5, as partial safety factor of concrete is 1.5. And for considering this shape factor, as there is a shape change from cube to rectangle, and it is elongated rather than a cube, right? It will be having a number of meters of length. To consider that, compensate that, we will again divide it by with 1.5, and design strength will be given as 0.466 FCK, and 0.87 Fi, that's final. So these are the two values you should remember. Okay, so this is the basic theory behind limit state method. That's it. And don't worry if you don't remember much of these things I said to you, or the details I said to you. You will have IS 456 to refer, and the values of partial safety factor gamma F will be available in page 68, and these things will be available in page 67. Okay, so then now we move on. Now we move on to stress strain diagram of a RCC beam. Okay, so this, if this is the RCC beam, you'll be having steel reinforcements like this, and this is the cross section. Okay, cross section, and you will have strain diagram like this. It will be at the midpoint from here. Okay, it will be somewhat like this. Okay, this joining point will extend this line to the end, and this line is known as neutral axis. Neutral axis. Okay, and this is stress diagram, and stress diagram is a little different than strain diagram. Okay, this is stress diagram. Okay, the thing is, of this cross section of beam, below this neutral axis, this is a neutral axis where there won't be any forces acting. If, as you know, this, if this is the beam and load is acting like this, this will be deflecting like this. The beam is supposed to reflect like this. Okay, so the top portion will experience what? Compression, and bottom portion will experience tension. That's why we are providing only bottom portion will be experiencing tension, right? Compression and tension. That is why we provide steel reinforcement on the bottom only. Okay, because steel can resist tension. Okay, compared to much compared to concrete. Okay, so steel resists tension. That's why we provide steel reinforcements like this. Okay, so there will be a neutral point. This is neutral axis, this dotted line. That means there won't be any force acting on the neutral axis. In the area above neutral axis, you will experience compression. And in the area below neutral axis, you will feel tension. But it won't be felt on the concrete, it will be just felt on steel. Only if the steel fails, that tension will be coming on to the concrete, because steel is the prominent element that will be taking the tension. Okay, tension will be taken by the steel, and compression will be taken from this whole area of concrete, and this distance we call it as XU. Okay, XU, and this distance will be, this is total distance is called D. This is not the total depth of concrete. This will be the distance between the top of concrete beam to the center portion of steel reinforcement, that is D. Okay, capital D will be the depth of concrete beam, small d is right till here, because the load acting is only till here. This portion is called cover portion. That portion is provided only to protect the steel reinforcement, nothing else. Okay, so all the strain and stress diagram will be up to only D, from top portion to D portion, steel portions. Okay, so this strain diagram, you have some assumptions. You assume that 0.0035 is the maximum strain that is experienced on a maximum farthest of concrete fiber, 0.0035. Okay, that is 0.35%. And similarly, we have another assumption that maximum strain of steel reinforcement will be 0.87 Fy, that is design load, divided by ES plus 0.002, where ES is modulus of elasticity of steel. Yes. Okay, so these are the two assumptions, and we know this is XU, and we assume that the tension is acting on this line and compression is acting on this whole area, like this. The stress diagram will be something like parabolic till some point and rectangular after towards the top. Okay, so it will be acting on this whole point. Okay, and we assume this tension acting this force as 0.87 Fy, that is design strength of steel. 0.87 Fy is the strength at steel, and we assume that the maximum point, at this maximum point, it will be 0.466 FCK, as we have discussed in the last. FCK divided by 1.5 divided by 1.5, 0.466 FCK. Okay, and as you know, this is a single line, so this will be an isolated point. You can just take it as that. But there, in here, there is a situation. 4/7 XU. This distance will have a parabolic shape, and the remaining 3/7 XQ will have a rectangular compression action. Okay, so solving all this, we will get this C as 0.36 FCK. Okay, we solve this to get, this is in here, it is 0, and as no force is acting on neutral axis, and at the maximum farthest string of concrete, layer of concrete, is 0.466, and the effective compressive stress is 0.36 FCK. Okay, so now we want to equate these two. Which two? Compressive force and tension force. Okay, So we want to equate compressive force with tension force, that is 0.36 FCK, that is compressive force acting on this area, that is this area. That will be what will be the area acting on into XU. XU is the depth and this will be B, and XUB will be the area of this compression acting area, and this will be the force into area stress. Okay, that is C, that is equal to what will be tension force, 0.87 F1 into what is the area, we call it as AST. AST is area of steel reinforcement, area of this surface. If there are 4 or 3 12 mm bars, we will just add those 12 mm with the area. Okay, pi r square or pi d square by 4 into 3. Okay, that is AST. And from this you know FCK, what is the grade of concrete, you know B, what is the assumed B, what is Fy, if it is 250 Fe 250 you can substitute as Fe 250, AST you can calculate simply. Now you can calculate what is the XU value. XU will be 0.87 Fy AST by 0.36 FCK B. Okay, I hope it's clear right till here. And next point, from IS code you will have a table in page 68 with standards of XU by D, XU limit by D for each Fy value. Okay, so that will, as it is XU limit by D, we will take it as XU by D 0.87 Fy AST divided by 0.36 FCK B into D. We will just put 2 D's on both terminals, that's it. And we will calculate this XU by D and then compare it with the XU limit by D in page 68 of IS 456, and then we will know something else. We will see what it is. If XU by D is equal to XU limit by D, then it is known as balanced section. That is, the strength of concrete and steel are equal. Okay, it is not over reinforced, it is not under reinforced. The strength taking capacity of compression and tension are equal. That's why it is called as balanced. Okay, as we know, there is a term called limit state at the starting of our topic. When that limit state attains, it will be attained at compression and tension simultaneously. It will just reach limit state at both ends simultaneously. Okay, and if next case, if XU by D is less than XU limit by D, then it is known as under reinforced section. Under reinforced section, that means when limit state occurs, steel reinforcement will fail first because it is the lesser one. Okay, when limit state occurs, steel will fail first. Actually, that is an advantage because, as I said earlier, concrete is like a chalk. It will just crush in a moment's notice. But in case of steel, it is a ductile material. It will elongate. So, if suppose a beam above me is failing, and if it is under reinforced section, it will show that deflection. It will deflect for quite a days of time and then fail. So I will have time to escape, to take my belongings and run for my life. Okay, so that is an advantage. So we want our sections, all our sections, to be under reinforced. Okay, I hope it's clear. If XU by D is less than XU limit by D, it is under reinforced section. That is, when limit state occurs, steel will fail first, and that is an advantage. And the last one, if XU by D is greater than XU limit by D, then it is called as over reinforced section. At limit state, concrete will fail first. So as I said, if the beam above me is an over reinforced section, I won't be getting any time when I am speaking to, I will be just dead. Thing will fall into my head because there won't be any deflection for concrete. It will just crush and the beam will fall down by failing at compression. Okay, so we don't want over reinforced sections in our constructions. It is preferable to have under reinforced sections. Okay, so that is about XU limit and XU max. Okay, and the last thing you need to know in this basic study of limit state method is moment of resistance there, or MR. Moment of resistance is what we are behind. Moment of resistance is the resistance offered by the beam against the loads. Higher the moment of resistance, higher will be the resisting power or strength of this beam. Lower the moment of resistance, lower will be the strength of or resistance to load of this beam. Okay, so we want more moment of resistance for any civil engineering structure. Okay, so for moment of resistance we have an equation C or T into lever arm moment of resistance. C or T, it is not divided by its compressive force or tension force into lever arm. Lever arm is the distance from this point from the compression point. Okay, this point to this point, or the compression, the distance between compression point and tension point. This is lever arm. Okay, so in case of balanced section, you can take moment of resistance as anything, C into lever arm or T into lever arm. We know what T is, we know what C is. Okay, it's just simple terms. Okay, you can take both because it is balanced section. It attains limit state at simultaneous time, at same time. Okay, C into LA or T into LA. In under reinforced section, moment of resistance will be equal to, yes, in under reinforced section, the limit state will be attained first by steel, right? So it will be only T into lever arm. Okay, and as you can guess, over reinforced section, moment of resistance will be equal to C into LA, because concrete will be attaining limit state first before steel. Okay, so don't you worry about all the equations about balanced section or under reinforced or over reinforced section. You have it in IS code. Okay, I am telling all this because you will be maybe you may be allowed to get in your examination halls using IS 456, but there is no point in having a book with all the data if you don't understand a thing. So understand the concept and understand the reasons behind all the things that you need to know, and then use the book as your resource. Okay, so you don't need to by heart anything that I have told you, but you need to understand everything. Okay, thank you.